So, can you hear me? Okay, so welcome back to the session of the tutorial. So here that is the news articles about our feature selection repository. So actually in this April that our repository is ranked the second one in the 5 machine learning projects that you can no longer overlook. So basically that you can try to download our repository and play with it. And here is, we also list the size of our tutorial. You can try to download the slides. So next, I will talk about some advances of feature selection research. So first, I will talk about what should we do if we have structures among features. So here that we mainly focus on this part. So although existing feature selection methods, such as lasso, has achieved a great success in many real-world applications, these methods actually do not explicitly consider the structures among features. So specifically that the different feature selection algorithms may yield the same result, even though that the orders of the features are reshuffled. So in many real-world cases that features may exhibit various types of structures, such as the spatial or temporal smoothness, and also that features can be divided into some disjoint or overlapping groups, and also that we may have tree or graph structures among features. So actually that structured features appear in variety domains. So for example, features may have the property of the temporal smoothness. So if we consider each research topic of a scholar as a feature, so basically we can see that his research interests change gradually over time. And the changes are very smooth between two stages. Another example is that features may form group structure. So for this brain image, if we consider each pixel as a feature, so we can see that each pixel is associated with a group information, and these groups correspond to different regions of the brain. And also that we may have the graph structures among features. So for example, that in this knowledge graph, we may have various types of relations among different entities, and these different relations form a graph structure. So at last, we can see that we may have tree structures among features, such as the different words or concepts in some lexical database, such as WordNet. These features are actually organized in a hierarchical way, form a tree structure. So actually that people have found that by incorporating these feature structures into detailed learning algorithms, it can help us identify more relevant features, and also that the performance of the most existing learning algorithms can be greatly improved. So here we give a general framework of the feature selection with structured features. So here that we make use of popular methods, which tries to minimize the fitting error penalized by a structural regularization term. So basically, from this formulation, we can see that X is a training data, and Y is a target variable. It can be a regression target. It can also be a category of the classification. And W is a feature weight. And we can use different loss functions, such as least square loss, logistic loss, or hinge loss. And the second term is actually a penalty term. The feature structure is encoded in G. So basically, this term says that if the structures in G is inconsistent with the feature structure basically that it says that if the structures in W is inconsistent with the structure in G, this penalty term, the value will be very high. So basically, we want to penalize this term. And alpha is a balancing parameter to make a control between the loss function and the penalty term. We can see that this formulation is actually very flexible in incorporating different kinds of feature structures. So we only need to design different terms for the different penalties to incorporate different kinds of feature structures. We will first talk about one of the most common structure among features, which is the group structure. Some examples can be the different regions of the brain, different functionalities, groups of the genes, and so on and so forth. So if features themselves have group structure, when we perform feature selection, we normally tend to select or do not select a group of features simultaneously. So here is the illustration. We can assume that there is a linear relations between the x and the y, and w is a feature weight. Suppose that there are 5 different feature groups, and there are no overlaps between different groups. So by performing the group lasso, so we can see that it actually performs a group selection by finding only a small subset of groups. So in this toy example, we find 2 groups, G1 and G4. So actually, once the group is selected, all the features in that particular group will be used for the model construction. So here is the formulation of the group lasso. The first term is the loss function. And for the second term, we can see that for each block WGI, we first impose a L2 norm on the WGI. And then based on the result that we impose the L1 norm. And here that HI is the weight for the ith group to show how important the ith group is for the model construction. And for the group lasso, actually, we try to select a small number of groups. And once the group is selected, all the features in that group will be used for the model construction. So however, that in many real-world scenarios, it is also desirable to find representative features from the particular selected group. So here that we have the sparse group lasso. So basically, sparse group lasso tries to perform group selection and feature selection simultaneously in a joint framework. So from this object function, we can see that this object function is very similar to the group lasso. The only difference is that we also consider L1 norm on W. So here is the result of the sparse group lasso. So basically, we can see that we find 3 groups, G1, G3, and G4. The blue group, the orange group, and the green group. And also that we achieve feature sparsity within the selected group. So for example, for the features in G1, only 1 feature is used. And for G3, that only 2 features are used. So here is a comparison between the lasso, group lasso, and the sparse group lasso. So basically, we have 4 groups between different features. And if we use lasso, so actually, we totally ignore the structures among features. And the selected features can be evenly distributed over different groups. And for the group lasso, we perform group selection to find a small number of groups. And the sparse group lasso can be considered as a trade-off between the lasso and the group lasso. So it first performs the group selection to find the small groups, and then it tries to achieve the feature sparsity within that particular selected group. In addition to the group structure, different features can also be organized hierarchically, forming a tree structure. So a motivating example is that in face recognition, different pixels of the face image can be organized in a tree structure. So for example, in this example, we can see that the root node of this tree is actually the whole face image. And then its child node can be different the facial parts of the face. And then the different facial parts can be continuously divided into some local patterns. And at the bottom level, that each individual pixel is actually a leaf node of the tree. And some other examples can be the organizations between the genes and the words, so on and so forth. The tree-guided group lasso is proposed for features that can be represented as the index tree. So here is a simple example of the index tree. So at the bottom level, that each feature is the leaf node of the tree. And actually that for the internal nodes of the tree, that it is a group of features. And each internal node in the tree is associated with a weight, Hij, shows how tight the features in its subtree are correlated. So in this example, we can find that the features in the child node is actually a subset of the features in its parent node. So once a parent node, if a parent node is not selected, then all the features in its subtree will also not be included in the model. So here that we have talked about the group structure and the tree structure. In addition to that, in many word applications, we may have pairwise the strong feature interactions among different features. Some examples can be the synonyms and the antonyms between different words in natural language processing, and the regulatory relations between different genes. And if there exists strong pairwise dependencies between different features, we can normally use the graph structure to represent such kind of dependencies. So in this graph, that each node represents a feature, and each edge represents an interaction between two different features. And also that we can use the affinity matrix or the adjacency matrix to represent such graph. So since that there exists strong dependencies between different features, so when we do the feature selection, these two features will tend to be selected together. And also that their feature weight will also be similar with each other. This target can be achieved by imposing a graph regularization term on the feature graph. So here is the formulation. So basically, the third term says that if feature I and feature j is connected by an edge, it will make the feature weight of the ith feature and the jth feature close to each other. And also that we have a sparse regularization term on W to achieve the feature sparsity. In the previous example, we can that it only considers the positive pairwise interactions among features. But in many real-world cases that features can also be negatively correlated, such as antonyms between different words in natural language processing. So here that the graph-guided fused lasso is proposed to explicitly consider the positive and negative interactions among different features. So from this formulation, we can see that if there is a positive correlation between feature I and feature j, basically this term will make the feature weight wi and wj close to each other. And on the other hand, that if there is a negative correlation, then rij is negative, and it will make w and wj far away from each other. So here that we give a summary about feature selection with structured features. So basically that this kind of method can incorporate different kinds of feature structures as prior knowledge into the model construction. And one advantage is that it can improve the learning performance in many cases. And also that since we explicitly consider the organizations between different features, it will make the learning process more human interpretable. However, that there are also some limitations. So the first limitation is that most of these algorithms in this family are supervised method and require label information to assess the feature relevance. And the second limitation is that we can find that most algorithms in this family, they are based on the L1 norm regularization. So basically, to solve this kind of L1 norm regularization, we need to solve some complex non-smooth optimization problems. And the computational efficiency is another difficult problem. So next, I will talk about how to design feature selection algorithms with heterogeneous data. So previously, that we have talked about some traditional feature selection algorithms. And these algorithms are only proposed for a single data source. And these algorithms are heavily based on the data IID assumption. this assumption says that different data instances are independently sampled from the same distribution. But nowadays, that heterogeneous data is actually becoming more and more prevalent. And the data IID assumption is often not valid in such kinds of heterogeneous data. So for example, that we can have the network data. The one motivating example is that users nowadays in social media platforms, they may post high-dimensional content information. And in addition to that, users, they are connected with each other by various types of social relations. Another example is that in many cases, we may have the data from multiple data sources. So for example, in the medical domain, we may connect different data sources to diagnose the disease of a particular patient. And supposedly that if we have data from multiple sources, that since we collect more data, so basically that supposedly it can help us to achieve better performance. But for each particular data source, we may have some noisy and irrelevant and redundant features. So therefore, that the existence of such kinds of features, in the worst case, they may contradict with each other, which is unfavorable for the learning. So it is very important to use feature selection to find some informative features to make the fusion of the different data sources more synergistically. So we first talk about how to design feature selection with network data. Network data nowadays is everywhere. So some examples can be the social networks, causal networks, gene networks, and transportation networks, and many more. So network data is actually distinct from the traditional data. So here that we give a toy example. So in this example, we have 8 data instances, and each data instance is associated with m-dimensional features. Normally that we can use a matrix to represent the data, where the rows represent the data instance and the columns represent the features. But actually that these data samples are connected with each other. So in addition to the traditional data matrix, we may have the adjacent matrix to represent the pairwise interactions between different data samples. So one natural question is that since in the network data, we have 2 different types of information, so why we don't just use one single data source to do some learning? For example, that if we want to cluster the users into different groups, we can just make use of his post information or his profile information to do some clustering. And in addition to that, we can also just make use of the relations between different users to formulate the problem of the clustering into a community detection problem. So why we don't do that? The major reason is that it is widely observed that the features in the nodes and the network structure, these 2 types of information are actually highly correlated. And this kind of correlation can be explained by some social science theories, such as the social influence and the homophily. And recent study has shown that if we explicitly model such kinds of correlations, the learning performance of many tasks can be greatly enhanced. Some typical examples can be the community detection, anomaly detection, or the collective classification. But apparently that not all the features are highly correlated with the network structure. Therefore, that it is very useful to use feature selection to find some informative features, such that these kind of features can be closely hinged with the network structure. And in this way that we can improve the learning performance of many learning tasks. However, that performing feature selection with network data is a very challenging problem. So first, that we are not quite sure how to model the link information to tackle the long data IID property. And the second challenge is that data from a particular data source may be noisy and incomplete. So therefore, that we need to design an effective manner to fuse different information sources. The third challenge is that in a network, the label information is often very costly to obtain, as acquiring these labels requires both time and a lot of human efforts. And in addition to that, some unique properties of the network and the features will also bring more challenges. So for example, that in social networks, the network structure could be highly noisy because the existence of the social spammers, they may generate a large amount of fake links. So how to tackle this challenge is also a very interesting problem. So here that we first talk about some representative feature selection algorithms with network data. So first we talk about some supervised methods by using the label information. And then we talk about some unsupervised method. So one of the first attempts, they try to use a linear classifier to capture the relations between the content information and the class label y. And they assume that the classifier is w, which is a linear classifier. And they impose the two-one norm regularization term on w to achieve the feature sparsity. And also that to model the correlations between the link information and the content information, they make use of the graph Laplacian. And here is the final object function of the proposed method. And they try to solving this problem. And after obtaining the model parameter w, then they can obtain the feature scores. So based on the feature scores, they can do the ranking and find some representative features. So previous method only consider one type of information on the networks. So in this work that the linked FS, they try to investigate the different kinds of relations on the social media data. So here is a total example of the social media data. So here that the UI represents a user and the PI represents a post. So basically that we can abstract 4 different types of relations from this graph. So we have the CoPoster relation, and the co-following relation, co-followed relation, and the following relation. And actually, these different types of social relations can be supported by these 2 above mentioned social science theories. And here that we specific on the CoPoster relation. So here the basic hypothesis is that the posts by the same user are more likely to be of the similar topics. So basically that their labels should be similar with each other. So therefore that they try to incorporate such kinds of the CoPoster hypothesis into the basic feature selection framework. And from the third term, we can see that for each user U, and if he has 2 posts, PI and PJ, so basically we will make the labels of these 2 posts close to each other. And they also perform some experiments on some social media data sets, such as blog catalog and the dig. And they have the very rich information in these 2 data sets. So basically, we have the post relations. We have the post, we have the users. We have the user-post relations, user-user relations, and also the class labels of the post. And in the right table, we can see that by incorporating such kinds of CoPoster relations, the learning performance is greatly improved. So previously mentioned 2 approaches, they assume that all the nodes in the network, they have a same model parameter W. But actually that in many cases, the content information of different nodes could be quite personalized. So for example, that the blogs, posts, or images of different users in social media, they could be quite diverse. And the users could have quite different social foci. And another example is that even the same content information may convey quite different meanings. So for example, if we have such kind of post, the price comes down hashtag Apple in the Twitter. And if the author of this Twitter is a student and wants to buy some Apple product, so this tweet may convey some positive sentiment. And on the other hand, that if the author of this post is a businessman and holds a large amount of Apple stock, then basically that this tweet may convey some negative sentiment. So in this way that we can see the content information of the different nodes in the network could be quite different. But But more or less that these nodes may share some commonalities to some extent. So here the question is that how to tackle the idiosyncrasy and the commonality of the node features for learning tasks, such as node classification. So here the solution is that we can try to build a personalized model by finding both the personalized features as well as the shared features by all the users. So how to find this kind of personalized features? So first, we assume that there is a linear classifier between xi and yi. Xi is the content information of the ith node, and yi is its class label. And we assume that this linear classifier consists of two parts. One is the global feature weight, W tilt. This global feature weight is shared by all the nodes in the network. And another term is wi. We call it a local feature weight. So basically that this local feature weight is specific to each individual in the network. So first, we want to find the globally important features. So we first impose the 2R norm on the global feature weight, W tilt. In this way, we can find the globally important features for all the nodes in the network. Then the problem is that how could we find the personalized features for each individual? So here that we make use of exclusive group lasso term. So basically that the exclusive group lasso says that it will regard the features of user as a group. And first that it will encourage the intra-group competition. So basically that we will find some features for each group. And second that it will discourage the inter-group competition. So in this way that the selected features will be evenly distributed over different groups. So in this case, we can see that for different user groups, we can at least find one features for each group. And these features are the personalized features for each individual. And from the above formulation, we can find if we want to learn the local feature weight, wi, we can only have one data sample, which is xi. So the model, in most cases, can be easily overfitting. So how to tackle this problem? So here the solution is that we can cluster the local feature weights into multiple groups to reduce the overfitting. So basically that if two nodes are connected with each other in the network, then we will make them borrow strengths from each other to learn the local feature weight. In this way that we will have more than one data sample to learn the local feature weight. And the overfitting problem can be easily solved. And here is the final object function of the proposed personalized feature selection. And we perform some experiments to compare it with some global feature selection method, such as the FSNet. So we can see that the personalized feature selection method outperforms the global feature selection method in most cases. And so therefore that we can see that it is indeed very useful to incorporate the personalized features in the feature selection. So here that we have talked about some supervised feature selection methods. And, but in many real-world cases that data in the network is often unlabeled. And without label information, it is difficult to assess the relevance of features. But fortunately that the link information is highly correlated with the content information and can provide us some additional constraint. So here is a simple method to try to leverage the link information for the feature selection. So in the first step, they try to make a use of a method called the social dimension, try to obtain the community structures of the nodes in the network. And then based on the social dimensions, they will obtain the within, between, and the total social scatter matrix. And their target is to make an instance within the same social dimension to be similar with each other. And also that make the instance between different social dimensions to be dissimilar with each other. And in addition to that, they also try to make a correlation between the content information and the pseudo-class label y. So by using the Laplacian. So here is the optimization framework of the proposed linked unsupervised feature selection. So basically that we can see y is a discrete variable. And due to its discrete nature, that it is difficult to directly optimize it. So therefore, that they further impose orthogonal constraint on W, and also that they add a L2 norm regularization term on W to achieve the feature sparsity. So however, that there is also some limitations about this method. So just as Jiliang has talked about that for the unsupervised feature selection method, we normally have two groups. One option is that we can obtain the cluster structure from the data and then perform feature selection. And another way is that we can embed the feature selection into the clustering to make these two phases complement each other. So motivated by this, that we also propose a method called the robust unsupervised feature selection, which tries to embed the latent representation learning into the feature selection. So in this way that if the network structure contains many noisy information, so in this way that good features can help us learn better latent representations, and in turn that the good latent representations can also help us to find good features. So I will not cover the details about this method, but we can show some experimental results. So here that we use two social media data sets, blog catalog and Flickr. And we have many noisy information in this kind of two social media data sets. And after performing feature selection, we can use the selected features to do the clustering. And normally, the higher the clustering performance, the better the selected features are. So we can see from the following two tables, the proposed robust feature selection method outperforms existing feature selection method, the first three methods. So it shows the necessity of using the link information for the feature selection. And also that it outperforms the method which separates the network structure modeling and the feature selection. So in this way that we can say that our proposed method is more robust to the low-AZ links. And previous method that most of them only consider the positive user interactions. But in addition to that, nodes in the network can also be negatively correlated. So for example, that in addition to the trust relations, we may also have the distrust relations in some product review website, such as Opinions. And also that in addition to the friendship relations, we may have the false relations in many social networking platforms. And we refer such kinds of networks with both positive and negative links as assigned social networks. And a recent study have shown that the negative links have some additional value over positive links in advancing many learning tasks, such as the recommendation, network embedding, and sentiment analysis. So it motivates us to investigate if the negative links can also help us find more relevant features inside networks. So actually, this paper was published in KDD this year, and we will have a poster session tomorrow night. And if you are interested, you can just stop by. So I'm not going to cover the details about this method. So in addition to the network structure, for the heterogeneous data, we may also collect the data from multiple data sources. So for example, in the medical domain, we may connect we can make use of the different sources to help us to diagnose the disease of a patient. So for example, we can use his blood test, cognitive measures, MI sequence, and some clinical measures. And in addition to that, for example, to analyze the United States election results, we can try to connect more data sources from multiple news media. And features, so basically that since we have multiple data sources, the features from different data sources could be not very good. And in the worst case that due to the existence of these features, different data sources could contradict with each other, so which is not favorable for the learning. And in this case, we would like to make use of feature selection to find good features to make different data sources such that the different data sources can be fused more effectively. And here we introduce the multi-source and the multi-view feature selection. So here that we show the difference between these two types of feature selection method. So basically, for the multi-source feature selection, it tries to find the relevant features on a target source. And normally that it does not consider the correlations between different data sources. Different from the multi-source feature selection, multi-view feature selection tries to find the relevant features across all the data sources. And so in this example, we can find for each different data sources, we can find some representative features. And in addition, different from the multi-source feature selection, it tries to leverage the correlations between different sources. So that's the major difference between the multi-source and the multi-view feature selection. They both can be applied on the multi-source data. So first, we talk about the multi-source feature selection. So in this method, that they try to obtain multiple local geometric patterns from the data. And based on the local geometric patterns, they obtain a global pattern, which can be calculated by the summation of different local affinity metrics. And they also introduce a concept called the geometry-dependent sample covariance matrix for the target source xi. So it depends. So it depends on your need. So if, for example, if you want to find the representative features, in previous example,
the boarding target and the source. So is it a part of data?
Yes, it's part of the data. So basically, we have multiple data sources. So in this left,
and there's no label information.
There's no label information because for the multi-source data, that normally it is difficult to find a consensus label information because different sources may contradict with each other.
Yeah, I think this is probably helpful for this having source.
So here the problem is that after we obtain the covariance matrix C, how could we find the features for the target source? For example, for the xi. And there are two methods. One method is that we can simply sort the diagonal of the C, and then we can return the features with highest variance. So basically, this method is equivalent to find the features that is consistent with the global pattern. But this method has some problems. So one limitation is that it is very similar to the Fisher score or the Laplacian score we have introduced previously. They cannot consider the redundancies between different features. So therefore, they apply a different method by using the sparse PCA to select features that are able to retain the total variance maximally. So in other words, this method can capture the interactions between different features. Different from the multi-source feature selection, the multi-view feature selection is often used to capture the correlations between different views. So as we mentioned that for the multi-source data that we often do not have the label. So here they introduce a concept of the pseudo label, which is F here. And they assume that there is a linear classifier between each data source and the F. And the model parameter is Wi. And for each data source, they try to impose a two norm regularization term to achieve the feature sparsity within each particular view. And also to learn the pseudo label they make use of the spatial clustering techniques. So this is the formulation of the multi-view feature selection. So this method actually assumes that different views are equally important for detailed learning tasks, such as clustering. But in many cases, the features of a specific view can be more or less discriminative for the learning. So in this example, we can see that the color feature, the color feature actually is more useful to detect the stop signs, while it is not very useful to detect the different models of the cars. So to considering this, that when we do feature selection, we also try to find some discriminative views for the for the learning. So here that they try to impose the interview and the interview feature sparsity. So basically, the last term is a group L1 norm regularization. It can perform the view selection by finding a small number of views. And the second term is performing the feature selection within that particular view. So here that we give a summary about the feature selection with the heterogeneous data. So the basic message is that when data come from different data sources, it is very important to use feature selection to fuse different data sources. And there are some advantages of such kinds of method. The first advantage is that it will make different sources to be complement each other. And the second advantage is that since different sources can complement each other, it can improve many subsequent learning tasks. So however, that there are also some limitations. The first limitation is that most algorithms in this family, they require solving complex non-smooth optimization problems. And this kind of optimization problems is often very difficult to solve. And the computational complexity will be very high. And the second shortcoming is that normally that we need to use the data matrix to store the data. And in many cases that it requires many complex matrix operations. And in some cases, we may even need to do the matrix inversion. So its complexity is also very high. So basically that these methods are very difficult to apply to very large scale data sets. So at last, I will talk about some effective yet efficient feature selection algorithms for the streaming data. So previously talked about we have talked about the feature selection algorithms for the conventional data, for the structured features, as well as for the heterogeneous data. And these algorithms actually assume all the data and all the features are available in the memory before the feature selection takes place. But nowadays that data is often not static, and we are often surrounded by a huge amount of streaming data. And this streaming data needs to be processed in real time. So we can see that if we use a matrix to represent the data, so basically the matrix can be expanded in 2 dimensions. So both the features can be both the feature numbers and the data numbers, data sample numbers can be increased. And in the worst case, that the size of the data samples of features can be infinite. So here that we give two examples of the streaming data instance and the streaming features. So for the streaming data instance, one example is that in the online spam detection, we may continuously accumulate new emails. And once the new emails are continuously arriving, that the importance of the features for the spam email detection may change over time. And for the streaming features, one motivating example is that in many social media platforms, that millions of posts are user-generated every day. And therefore, that many new slang are created every day in these social media platforms. And these slang words quickly grab user interest and become very popular within a very short period of time. And it is not practical to wait all the data instance or features are available to perform feature selection. And in addition to that, it is also not easy to perform the batch mode feature selection each time when there are some changes, because the changes can be very transient. So the conclusion is that it is more desired to perform the feature selection in a streaming fashion, such that we can gain insights from this streaming data on the fly. And first, we talk about how to handle the streaming features. So basically, that in this case, the number of instances is considered to be fixed, while the candidate features are continuously arriving in a streaming fashion. And we refer such kinds of feature selection method as a streaming feature selection. Basically, that they have 2 steps. The first step is that we need to check if we need to accept this newly arrived feature or not. If we do not accept this new feature, we can just discard it. And on the other hand, if the new feature is accepted, we just include this new feature into the selected feature set. But here that a problem arises. The problem is that the acceptance of this new feature may make some existing features to be outdated and become redundant. So therefore, that we may also need to check if we need to delete some existing features or not. So actually, this step is optional, and and some algorithms do not implement this step. So one of the first streaming feature selection methods is called the grafting. So grafting is proposed to deal with models that can parameterized by a feature weight W with L1 norm regulation. So basically, this is the lasso problem. And the key part is that when new feature arrives, how to update the model parameter W. Here, that the key observation is that when we have a new feature, so basically for the second term that we will have, it will increase, which is alpha times the absolute value of the Wj. So here the problem is that how could we decide if we need to accept this feature or not? The basic principle is that we may only need to accept this new feature if its acceptance can reduce the overall object function. So basically that we need to check if the reduction in the loss function will outweigh in the increase in the penalty term. So based on this observation, then we can obtain the condition of accepting this new feature. So basically, we just need to perform the following gradient test. And if the condition is satisfied, then we just accept this new feature. Otherwise, we just set its feature coefficient to be 0. And as mentioned previously, that when a new feature is accepted, we also need to check if it will make some existing features become redundant. So therefore, when a feature is accepted, we further need to apply the conjective gradient descent to optimize the model with respect to all the current model parameters. And this step will result some certain feature weight to be 0. And then we can simply prune the corresponding features.
So what's the alpha here? What's the alpha?
Alpha is the parameter of the lasso. And assume the above proposed method actually assume that in a streaming case that the label information is available, but it is often not the case, as the label information is very difficult to obtain, especially in a streaming environment. But fortunately, that link information is prevalent in many scenarios and can provide us some additional constraint to guide feature selection. So here that we make use of assumption that the link information is relatively more stable once it is established. So for example, that even though that in social media platforms that many new slang words are created every day, but once for a particular user, once its friend cycles is established, it is within a short period of time, it is not likely to change. So basically, that based on this assumption, that we propose the unsupervised streaming feature selection method by making use of the link information. I'm not going to cover the details of this method, but we can see the experiments that we compare the unsupervised method with some state-of-the-art unsupervised feature selection method, and all these methods are actually batch mode feature selection method. And they have to, so basically when there are some new feature arrives, we basically have to apply these methods again. So we can see that the proposed unsupervised streaming method is much faster than this batch mode method. In addition to the streaming features, that we may also have some streaming data instance. And this problem setting can be regarded as a orthogonal setting of the previous problem. And in this problem setting, that the number of features is often considered to be fixed. So here the problem is that we need to design some online algorithms to update and maintain the up-to-date relevant feature subset. And here is one of the first attempts. So basically, it is designed for the binary classification performance, but problem in a data stream. And they assume that we have a collection of sequence of data sets, x21, xt, and each data two classes, either -1 or +1. So basically that they try to maintain a linear classifier to make a classification for the newly arrived data. And also that to achieve feature selection, it will make a truncation on the WT to only keep the k most important features. And in the following stage, that at most the k features will be used for the online binary classification. And here is the workflow of this proposed method. I'm not going to talk about this. Sorry about that. And at the last, I will talk about how to perform the feature selection on the data stream in an unsupervised scenario. And this case is more general, as the label information in most cases is difficult to collect. And the basic idea of this approach is that they make use of the state-of-the-art technique called the matrix sketching to maintain a low-rank matrix to approximate the currently observed data. And then, based on the sketching matrix, then can apply some regression to obtain the scores of each feature. And after that, they can do some ranking. And so here is the formulation. So we assume that xt is a normalized data matrix that is connected until time step t. And then we can get its rank k approximation by using the singular value decomposition. And here that they propose a feature selection method based on the MCFS, which Jiliang has talked about. So basically, MCFS try to obtain the clustering structure from the data first, and then make use of the cluster structure as the regression label, and then impose the L1 norm on the WT to achieve feature selection. But apparently that solving such problem at each time step when we have new data samples is very time consuming. So in that paper that they have observation. The observation is that when the matrix xt is orthogonal, so basically in this case that the ridge regression can replace the lasso. And in the next figure, we can see that they plot some results of the lasso and the ridge regression. And their observation is that the performance of the ridge regression and lasso are very close to each other. But on the right figure, we can see that the ridge regression is much more efficient to solving the lasso problem. And so their target is to try to find such an orthogonal matrix xt, such that they can convert the lasso problem to the ridge regression problem. And fortunately, that they find a method, which is the matrix sketching. And the matrix sketching is try to find the low-rank matrix to approximate the currently observed data, such that the product between the BT transpose times BT will approximate the XT transpose times XT. So basically, BT is a low-rank matrix which can approximate the XT. And in this way, that they can replace XT by the BT in the ridge regression. And also that the regression target can be adjusted. So basically, they only need to solving this problem at each time step. And this problem is much easier and more efficient to solve. And after solving this problem, they can obtain the feature scores by using the max pooling function. So basically, the higher the feature score, then the more important the feature is. So here that they show some results on the clustering compared with some state-of-the-art unsupervised feature selection method. So from the first figure, they show that their method, even though that they adopt some approximation strategies, their method can approximate this state-of-the-art method in terms of clustering. And also that they try to show the scalability of the proposed method. And they show that their method is much efficient than the batch mode feature selection method. So at the last, I will give a summary about this kind of method that is proposed to deal with the streaming data. So actually, that streaming data is becoming more and more prevalent in many real-world scenarios. And since that the data is continuously arriving at an unprecedented rate, so feature selection in this case should be supported in an online fashion to gain insights from the data. And there are some advantages of such kind of method. One advantage is that it is more efficient than the batch mode feature selection method. And also that it can well tackle the concept drift problem in the data stream. But also that there are some limitations. One of the first one is that most algorithms in this family, they need to some additional model parameters to tune. And actually, these model parameters is very difficult to tune in a streaming environment because it is impossible to do the cross-validation. And also that we can see that label information in many cases still plays a very essential role for the streaming feature selection. And how to perform the feature selection in a streaming environment without using the label information is still a very challenging problem. So at the last, I think we will talk about how to evaluate different feature selection algorithms. And we will also talk about some open problems when we applying feature selection. And at the last, we will give a summary. And first, I will talk about how to evaluate different feature selection methods. So basically that to evaluate feature selection, we first need to obtain the features. There are two categories of methods. The first category, we call it a feature weighting method. So basically, for this kind of method, we have to specify a desired number of selected features, which is k. And then we can rank features according to the feature score and return the top k ranked ones. And on the other hand, another type of method, we call it a feature subset selection method. Different from the feature weighting method, feature subset selection will directly return the obtained feature subset. So in this case, that we normally cannot specify the number of k beforehand. And also that we cannot guarantee the number of selected features. And here we talk about how to evaluate the supervised method. So basically, for the supervised feature selection, in the very first step, we try to divide the data into the training set and the testing set. And then we can perform the feature selection on the training set to obtain the selected features. And after that, based on the selected features, we can obtain a new data on the training data and the testing data. And we can then feed the new training data into a classifier, such as the SVM or the neural network. And after that, in the last step, we will obtain the classification performance on the new test data. We can use some classification measures to measure the performance of the feature selection, such as the F1 score or the AUC. So normally that if we obtain a higher classification performance, it normally indicates that the selected features are better. The evaluation of the unsupervised method is a little bit different from the supervised method because we do not have the label information to guide the selection phase. So basically that we can make use of the whole data set to obtain the selected feature sets. And based on the selected features in the second step that we can obtain the new data, which is the TS. And then we can perform the clustering on the TS. Given a number of clusters M. After that, we can compare the obtained clustering results C prime with the ground truth label C. It should be noted that in this case, the label information is only used in the evaluation phase, and it is not used in the selection phase. And in the last step, we can obtain some clustering results. Similar as the evaluation of the supervised methods, normally that the higher the classification performance, that the clustering performance, the better the selected features are.
Yes. Okay. Very good. The answer is yes. The very first one is about scalability, right? So if you think about the scalability, so the open problem one is the scalability. And the data size grows faster and faster, and Jundong already mentioned about streaming feature selection, but there are many new cases, and you still need to focus on. So, but this is like a very, what should I say, practical problem when you face real world data mining. But the second one is about scalability of number of features. When you have a lot of features, I think one person in the audience already asked the question when Jiliang presented his case, his part. It's about it's a cost of dimensionality, you see. And then in order for you to select the features, you still have to make use of the data. So how can you to solve this problem, right? So most existing feature selection algorithms have a time complexity proportional to this big O of d square. D is the number of dimensions. So this is also related to when Jiliang presented some people about like how simple it is, because you still have to calculate the covariance matrix. And for many feature selection algorithms, efficiency deteriorates. It's obvious. And so how can we do that? So this is a second scalability. Then if you also work on some specific problem, data mining problem, you want to actually, you don't like to see like this time I give you this set of features, and if you run the algorithm again, you get another set of features, right? So it's called a stability challenge. How can I find the set of features? And that makes sense. Also, that will give domain experts confidence. For example, a lot of people now working on this health-related issues, right? Healthcare-related issues. So a lot of people don't like, you give them like a different sets of features, so you say they all perform equally good in terms of accuracy. So remember when Jundong talk about performance evaluation, you use accuracy, the assumption is if performance in terms of accuracy improves, then these are good features. But if you have a lot of features, then you will see multiple sets of features, they can equally help you improve performance. That's why I was so confident when I presented the introduction part. I said that if you apply feature selection, you will see the performance improvement, okay? But so many people, right, from all over the world, you try feature selection differently. How can you all get a feature or get a performance improvement? The key is there are many subsets, they are correlated to each other, okay? And they can provide good performance. So for data miners, if we want to convince our domain experts, we really need to work with them and then find these subsets, features that make sense to them. Then they will help us to advance our goal. So this is a stability issue. Basically, you can have different samples of training data and then try to select features and then see how different these different sets of features are. Okay, so you can perturb the training data. This is the one. It's not easy. It's really not an easy problem, but it's worthwhile to do if you work on real world problems. And interpretability or understandability of features is a very, very important issue. But stability can help you in this direction. So how do you achieve stability? And it is for basically the key point here is for supervised method, because you have labels to guide you have labels to guide the search, right? But for unsupervised method, it will be a bit more difficult. And so now, remember, we also had a question about how can you know what's the number of features if the value the score value is continuous? And Jiliang promised that that's an open problem. And it is an open problem. In the beginning, we mentioned that the curve, it looks like this, but nobody knows where the optimal point is. So how can we do that? How would you do that from a computer science point? Is there any, like a simple method? There should be, right? So now you have so much computing power. What can you do? You can always try binarization method. You just estimate something very big. You assume this is, of course, it will be something like this. The curve will be something like this. If you make it like a very, very large, then you half of it and half of it, you can heuristically find them, okay? But it's a still open problem. How can you find it and with a theoretical bound? It's not easy. So this is called a model selection. And then model selection for unsupervised learning will be even more difficult, right? So we also list some different ways of doing this here. And the key is label information provides constraints. But without label, it is anybody's game, so it's more difficult. It's reasonable. So most of the time, we don't have label. And how can we work on this? This is another open problem. So this is the last open problem we can think of, okay? Cloud computing, right? Now it's cloud computing, and we share the data over the cloud. And then how can we do this, do feature selection? So what do we want to, some features are sensitive. So if we can make sure that the sensitive features, remember we just mentioned about a lot of sets of features, they are correlated. But so if we know these sensitive features, we select the sensitive features, but we also know the features correlated to them, can we just share that set of features instead of the set of features they are sensitive? See, that's another problem, right? And also, we talked about a lot of data. So think about this problem. If you have a limited number of features and you have a lot of instances, then regardless of what you are going to do, to hide the features, people can figure it out. There are many examples of this, okay? They can figure out the feature values. So this is another issue about how can you hide or do something about the instances so that you won't accidentally reveal sensitive information. So there's something called the differential privacy concept you can try, and to make sure that for features you want to have maintain this privacy, and for instances you also maintain privacy. I think that's the last is almost the second to last slide, okay? So, for those of you who stay until now, we thank you, okay? I know, it's not easy, huh? This is the first day of the conference. Just imagine the last day of the conference. I hope you can still have the energy like today. But because there are so many talks afterwards, I just want you to forget about everything you have. Don't worry about the slides, and think about what we talked about today. Number one, feature selection is useful. It works, okay? Right? It works. Number two, where can you find feature selection algorithms? Scikit-feature, okay? So, scikit-feature If you find the scikit-feature, you will find the tutorial and the slides and everything, okay? And so for today, I think Jiliang and I, we talk about the traditional ones for the first half of the tutorial. And Jundong talk about the second half. It's all about the new stuff. That's why Jiliang said that he belongs to 5th generation. But it makes me look very, very old. And so you structured features, heterogeneous features, and the streaming features. You see a lot of work to do, right? And so you won't be alone. We will be there. Jiliang got a new NSF grant working on feature selection. So even if we don't have 6th generation in my lab, and there will be 6th generation from his lab, okay?
5.1.
5.1, okay. And so the open source feature selection, it's open source. And you are welcome to contribute, and you're welcome to make use of it for your research. And so I said this is like almost the last one, but you don't need to really worry about this set, this slide. Just to remember the curse of dimensionality. Huh? When you want to convince people say deep learning can solve everything, you just say curse of dimensionality. Then you say feature selection can help deep learning, okay? And we provide a lot of references, okay? But this is the acknowledgement slide. This is really the last one. Okay. We also have a member very, very young. I think he was born last year or something, the year 2016, I think. 1 year, now it's 2-year-old, from Turkey. Okay. And these are the groups. I think we didn't have time to put up a Jiliang's group. That's 5.1. And the funding agencies, of course, without funding agencies, we won't be able to conduct research. But we do basic research. Okay, we only do basic research. And thank you very much. And we will be here. And if you have questions, feel free to come by and ask, or just shoot us email. All right? Thank you.